Thanks again for the kind introduction. I'm really happy to give a talk at CP about differential privacy, and I'm going to talk about the role of constraint optimization in differential privacy, as well as I will shed some lights on some undesired effects which arise when we make decisions using privacy-preserving data. So this talk is based on the results of a collaboration with Pascal and his students, KU, and my students, Quantron and Maitin. So optimization and learning systems have become instrumental for many decision and policy operations that are involving individuals. You may think at assisting in legal decisions, determinations related to whether an individual qualifies for given benefits, such as loans, or assigning resources to entities or individuals. So those are just a few examples. Often the success of this is associated to the presence of rich data sets containing personal identifiable information. And so the use of those data sets combined with the adoption of black box algorithms has sparked concerns about how those systems operate. And two key concerns that are regarding how much information those systems leak about the individuals whose data is used as input, as well as how do they handle discriminations. So for the first concern, privacy, differential privacy has become the paradigm of choice for protecting data privacy, and its deployment are growing at a fast rate. They involve the release of many data products by the 2020 US Census, which are about to be released. Google Gboard, which is a virtual keyboard using predictive type engine, which uses differential privacy and federated learning to train their model privately. Facebook has used differential privacy to release large data sets to support academic research on social media in the elections role. And Apple has used differential privacy in many features by default from its iOS 11, Uber, and so on. So differential privacy is really appealing because it bounds the risk of disclosing sensitive information of individuals participating in a computation. And the process, which is made to render the data or a model privacy preserving, however, might affect fundamentally some important data properties, which include the constraints whose data should satisfy, as I will see next. It was also recently observed that differential privacy system might induce biased decisions and unfair outcomes for different groups of individuals. And so the resulting outcomes can have significant societal and economic impacts on the involved individuals. And so this talk builds on those key observations, and I will discuss two key aspects of privacy-preserving tasks: accuracy and fairness. So here is the setting. We have a data set which contain data of sensitive data of individuals, which we want to protect. And we are using a privacy-enhancing algorithm M to release a privacy-preserving version of these data sets. What we want to do, what we care about, is the accuracy of this released data. So the private data needs to preserve some salient characteristics of the original data. In other words, if the data obeys some constraints, we want the resulting privacy-preserving data also to obey those constraints. And in addition to this, this data here does not really live in a vacuum, but in addition to this, there is another setting, and we are interested in understanding what are the effects of this data set here into a problem of interest. And in particular, we are going to analyze some allocation problems, and we're going to understand what are the effects of the privacy-preserving release data onto the disparate impact that might be caused by this allocation problem. So to give you some practical example, let us consider the following allocation. So the Title I of Elementary and Secondary Education Act is one of the US largest programs offering educational assistance to disadvantaged children. In 2015 alone, it distributed about $6.5 billion through basic grants. And the federal allotment is divided among qualifying school districts in proportion of the counts of student, size, children aged between 5 and 17 years old, who lives in families that fall below the poverty line or receive some form of federal financial aid. Now, the allotment is essentially formalized as follows. So we are apportioning this amount of money, and whether this AI here is just some student expected student expenditure in that district. Now, the plot here illustrates the expected disparity errors that are arising when we're using private data as input to this allocation problem. And so these errors are expressed in terms of US dollar misallocation across different New York school districts ordered by their size. And so we can see that some school districts might receive substantially less amount of money than warranted, which may result in large fairness issues. Let us start with the following setting. We're gonna see how to release data privately. First, some motivation. So every 10 years, the US Census Bureau surveys the American population with the goal of counting every person living in the United States and collect information about them, including gender, age, race, and ethnicity. So the decennial census is unique because it's an actual enumeration of the total population living in the US. It's not a sample. So this data collected by the census is important as it determines the number of seats each state has in the US House of Representatives based on a share of the population. It is also used to distribute billions of dollars in federal funds to local communities. So accurate counts is really important. But because of the importance to have an accurate count, Congress makes this data collection mandatory, and we're also regulated, the privacy of this data collection process is also regulated by Title 13. And this is not only for an ethical reason. In fact, fear of privacy violation induces a body of the population not to answer or to alter their answers for some questions. So there was a controversial question here in the US about citizenship, which was requested by the Justice Department in the previous administration. And the fear that people would not complete this questionnaire, it's backed by evidence. So places that were hard to count were those with predominantly Hispanic or other minority population. And so when insufficient statistics are collected, the census personnel needs to be sent door to door to collect this data. And this is a costly process. So for example, California had approved a $100 million budget in order to hire workers to do this process. So guaranteeing privacy here, it's important for both an ethical and an economical reason. So how do you keep survey data private? Well, the census has used some disclosure avoidance techniques since the 1940s, but the short answer is really that you cannot. In fact, there is a famous theorem that tells us that every bit of information that you release, no matter how small it is, it contributes to violate the privacy of the individuals participating into the data set. And as evidence to this threat, the US Census had carried an attack on its 2010 data release, which is called a linkage attack. So what is a linkage attack? Well, the 2010 data was anonymized by using the techniques used since the 70s. And this attack tried to re-identify the correct statistics or the presence of an individuals into this data by using only auxiliary information which is publicly available. And so it turns out that you can reconstruct the census block count correctly. You can reconstruct block count, sex, age, gender, and ethnicity exactly for 142 million people. And if you're allowing a slack of 1 year, then this number bumps up to 219 million people. And you can re-identify uniquely 118 million people, so 1/3 of the population, including their name. So obviously, Title 13 here, it's broken. So what can we do to protect privacy of this information? Differential privacy comes to rescue here. And so let's see what is differential privacy. Differential privacy is a property of an algorithm that bounds the risk of re-identification. So the definition is as follows. Imagine we have two instances of a word. We have a word, the one where you have a data set, the one where there is some data that does not contain your information. And then there is another word where you have another a data set, D2, which is exactly a copy of D1 that in addition contains your data in it. So differential privacy tells us that a randomized algorithm is epsilon differentially private if for any of these input data sets and any possible outputs, the probability of generating those outputs from a data sets coming from the word D1, where you were not in, it's very similar from that of generating the same output from the word where your data was in. And this similarity here is measured in terms of epsilon, a constant. So the intuition here is that an adversary that takes a look at the output of the computation, O, should not be able to distinguish whether that output was done by taking as input a data sets D1 where you were not in or D2 where you were in. So in more details, what does this mean? Well, let us consider an example. Let's say that you want to compute some statistics, maybe the average population of this cohort. Let's say that you have an output in your mind, let's say 32, and then you're computing what is the probability of this event, that the probability of this particular cohort has age 32. Then you're adding your data in it, and you compute again the probability of this event. And then if you can bound this ratio of those two quantities by a constant for any possible output in any possible data set, then this algorithm preserves differential privacy. And so epsilon here is the risk of a user for joining the data set. And so differential privacy has a really cool property because we can really bound the risk of privacy, but also has other notable properties. In particular, it is immune to linkage attacks. So remember the sensible linkage attack that used auxiliary information to extract some of its data? Well, now we are immune to this type of attacks, and also this is forward-looking. So any auxiliary knowledge that can be accessed in any time in the future won't be able to break the guarantees that we're offering right now. Composability, so if we are having two algorithms that are epsilon differentially private, then we can compose them, and the resulting composition will enjoy two epsilon differential privacy. And so this is important because we want to think about primitives and use those primitives to construct more complex algorithms. And finally, post-processing immunity tells us that if an algorithm gives you an output which is differentially private, then you can take that output and post-process it with any arbitrary function, and the result of this post-processing will still preserve differential privacy. So you're not going to break this privacy property. So how do you satisfy differential privacy? Let us imagine we want to release census counts of a population. So a simplified version of the census data release problem. What we're going to do is we're going to count the number of people in census blocks, in counties, in states at the national level. So we go at each census block and start counting. And so, for example, in this illustration here, we have Stanford census block. So you can see that this slide was previously presented at CP19. And so we're counting the number of people present in this area. We're adding noise drawn from a proper distribution. In this case, we're using a Laplace distribution with parameter delta Q over epsilon, where delta Q is the query sensitivity, which defines the maximal change of the output that we can have if we're adding or removing one individual into the data set. So here the query is just an identity because we're inputs are counts and outputs are counts. And so if we're adding one element to the input, the maximal change that the outputs can have is just one. So delta Q is one. So just adding noise from this distribution will result in an output which is epsilon differentially private. We move on. We'll do the same process for counties, and then for states, and then at national level, and so on. Now, observe that now an issue occurs when we're releasing all those numbers. Because the noise is applied independently at each count, the noisy quantities at the state level are inconsistent with very high probability with the sum of the noisy quantities at the underlying county levels. And so those constraints here that are inherent to the data because of the hierarchical structure that we have here are violated at each level of the hierarchy. And so similar issues also arise in other domains. So for example, in mobility, we study the problem of releasing private data to feed to an optimizer. We would select a dispatch for the vehicles to serve an entire population under some required quality of service constraints. So the data to be released here is the number of trip requests from an origin to a destination within a given time window. And each trip can be served with different transportation modes, such as shuttle, buses, or walking. And then there are different transit regions where the shuttles can be dispatched and allocated to pick up passengers. So those are all important features of the data and the problem that we would like to preserve. And so what happened here, when we optimize this system, so which means we're computing the resource that we need in terms of buses and shuttles to serve trip requests, with using the original data, we get a budget of 5.6 million. This is based on some estimate of a deployment in the University of Michigan campus. So you get this budget, 5.6 million. When you're using a privacy-preserving data set with a privacy budget that is conservative enough, this budget here bumps up to 20 million. And so this was actually one of the first applications that we studied about differential privacy in the context of optimization. So when we were looking at those numbers, we were really suspicious. And so an inspection here revealed that the number of total trip increased from an original almost 38,000 to 261,000. And so why this is happening? This is happening because this origin-destination matrix pair is really sparse. And so because you need to protect every single count, you're ending up adding noise to these zero counts. And because those counts can only be non-negative, then you're going to bias this distribution to the positive side. So this is a further consistency issue that we're having when we're using differential privacy for optimization problems. And a further problem that we studied was that of energy network optimization. So in this problem here, we're interested in optimizing the dispatch of the energy network generators so to serve some demands and satisfy the physical and operational constraints of the network. This is a nonlinear problem that we're solving. The data that this problem receives are the customer's loads, which contain sensitive information. In particular, load fluctuations may reveal information about the strategic operation of certain customers, and thus we want to protect them. Now, when we apply a Laplace mechanism, so Laplace noise on top of this data in order to create a privacy-preserving data set and use it to optimize some systems, what we observe is not only the error increases in terms of the objective cost, and this is because the resulting demands were consistently higher than the actual demands, but we also get significant consistency issues. So those are the numbers of satisfiable solutions that we can generate over some samples of data sets that we generate. And so here, essentially, we were producing private data sets that were not representative of the actual optimization problem. So the issue is really that differential privacy is oblivious to the structure of the data sets and constraints of the underlying problem, if used as it is. So what can we do? Well, in general, in a general context, we are interested in solving an optimization problem of this form. We have a minimizer, f of x, which is parameterized by some data component subject to some constraints, which are also parametric by this data set. And these data sets contain some sensitive information. So what we want to do is to use a privacy-preserving version of this data set to solve this optimization problem, but we also would like to preserve some fidelity. And so what we've done is introducing a concept which we named constraint-based differential privacy, which works as follows. So you first release a privacy-preserving data set by using a mechanism of choice, and then we're casting the problem of ensuring high fidelity to an optimization problem which has this form. So we want to find a new data set which is as close as possible to the noisy private data set while satisfying the parametric problem constraints with respect to this new data set. And if we are given an objective function value, so if this is public information, then we can also constrain the objective value computed over this new data set to be as close as given by a requirement to this publicly known value. And then we can release this data set here. That's a fancy animation there. So we have some desirable properties. Well, first, this mechanism guarantees privacy. And this is simply because it's essentially a post-processing step that uses only public information to do so. It is efficient when the space of constraint is convex, simply because this is a convex problem that we're solving. And for complex problems, the error induced by solving the optimization model that I described in the previous slide is no larger than that introduced by the Laplace mechanism, which has been proven to be an optimal mechanism and expectation. And so some intuition, essentially when you're given a query, so some data points, these data points, they lie generally in the space of constraints. And the addition of noise to these data points here might bring them out from their constraint space. And so what we're doing here is really solving a least square minimization problem subject to some constraints, which is a projection. And so we're projecting those points back to the closest feasible solution. And thus, as expected, the distance from the noisy point to the original one is at least as much as that of the optimal solution of our problem to the original point when C is a convex space. When actually the constraint set is non-convex, we can still bound this distance by a factor of 2. So what does this mean in practice? Well, on our energy optimization problems, we can have results which enjoy 1 to 2 order of magnitude improvements on several privacy settings. So those are essentially the results that we're obtaining by first solving this constraint optimization problem and then using an optimizer, so in this case, the energy optimization problem, the optimal powerful problem, to output a solution. And those are instead the valid solutions, so those data sets which report satisfiable solutions, and we're using their cost here to assess their differences. But in addition, we not only are improving their results in terms of cost objective, but we also get solutions that are satisfiable, so we satisfy the constraints. We get very similar results for mobility analysis, so the trip errors decreases of at least 1 order of magnitude with respect to using off-the-shelf algorithms, and the system costs stay really as close as the cost of the original system. So this seems to work great in some context. Now let's take a look back at the census problem, and if we apply this process here in it, so let's see what happens. So essentially, we're producing this privacy-preserving counts, and then we're redistributing this noise with our optimization problem here. So we're finding a new set of counts that satisfy those hierarchical constraints, so the sum of the children is to be equal to the value of the parent. But also we would like those numbers to be within some integer domain. And so this now causes this problem to be a quadratic integer problem, which is intractable for our data sets of interest. And so typically those constraints are relaxed. And but now this results in some issues because, well, the final solution might still violate consistency and faithfulness conditions after rounding. And also the mechanisms can still be too slow for very large data sets as those of interest to the US Census, which has over 300 million entries. So in a recent work, we have improved upon this method here by simply relying on the following intuition. So if we rearrange this original hierarchy to create as many subtrees as the numbers of group sizes that we have in each region, county, state, and so on, then the structure of the problem becomes evident. In fact, all those subtrees here they represent the hierarchy of counts for certain given sizes, and the hierarchical constraints in each of subtrees are independent from those of other subtree. Actually, those are conditionally independent only from the value of the root. And so this gives us a lot of structure to act with. And this allows us to create an algorithm that exploits a dynamic programming solution, which works as follows. So we first release privacy-preserving counts to associate to each node of this tree, and then we construct. So each node will construct a cost table that maps its possible values, so values in its domain, with a cost. And this cost, this tau cost, will represent the optimal cost for the post-process count size in the subtree rooted at this node when it chooses value v, right? And so the key observation here is that this function can be computed from the cost table of the children. So we can do this process recursively. And the dynamic programming works in two phases: a bottom-up phase, where we can compute the cost table from each node, starting from the leaf of the tree and propagating them up. And then a top-down phase, where the root node computes its table, chooses its optimal post-process value, and sends the values to its children until the process reaches the leaf nodes. Now, in the implementation of this program here is computed as a table constraint, but the issue is that we still have many of those problems to solve. We have really many nodes in our tree, and thus each subproblem is still an integer program and still intractable for the problem of interest. And so here there is another observation that we made, which is that these cost tables here are actually convex piecewise linear functions. And convex piecewise linear. And what happened is that joining cost tables from the children by solving this type of optimization problem also results in a convex piecewise linear function. And thus, we can construct a polynomial algorithm for constructing the nodes of those tables. And so all in all, we can get a really efficient method, which is boxed here, and where we are comparing the runtime of the algorithm with respect to the other dynamic programming version we use as table constraints. We can get up to 5 order of magnitude improvements in terms of runtime. And even if we're comparing it with the relaxed version of the problem, so the inexact relaxed version, we still get 1 order magnitude improvement in terms of runtime. And when we're looking at the errors, the lower the better, and we're comparing this boxed version here against other version, including the relaxations, we still get fewer errors and no constraint violations. So this was great and gave us pretty interesting solutions. But so far, we have talked about the effect of privacy on the fidelity of the problem. So how to satisfy this type of implicit constraints that arise from the data of the problem. But I mentioned earlier that there is also a second concern that we care about, which is fairness. So let us revisit the original setting. So we have our data set with sensitive data, and we're using a privacy-enhancing algorithm to release a privacy-preserving data set. Now, we can use a post-processing step, like the one that we have used in the previous slide, in order to create a consistent data set, Int'l. And then this data set do not really live in a vacuum. We want to use them in some optimization and some allocation problem. And so we want to understand the following. So because random noise is added to the original data set, X, the output of this problem, Px induce some error. And the goal is to characterize the disparate impacts of this error among the problem entities. And we are characterizing this impact here by analyzing its bias, which is the difference between the expected value of the problem outcome when we're taking as input the privacy-preserving data sets versus the problem outcomes over the original data set. And the expectation here is drawn over the noise of the mechanism, over the randomness of the mechanism. So we're saying that a mechanism is fair with respect to a problem if for every entry, the bias is the same. So if we, let us first focus on analyzing the structure of the decision problem. So if we take back this motivating problem, the Title I of Elementary and Secondary Education Act, notice that here the errors are expressed in terms of bias on this axis here, and we were noticing that there were some pretty significant misallocation in terms of spending. We noticed that some districts, namely smaller district size, they get positive bias, while larger district size, they get negative bias. And so we're asking, why is this happening? Why this bias is disproportionate? So the first surprising result that we had was that even if we're using an unbiased differentially private mechanism, so even if we're adding just unbiased noise onto the data set, the shape of the decision problem characterizes the unfairness of the outcome. And so this is because the bias can be approximated as an expression that involves the local curvature of the problem, P, as well as the variance of the noisy inputs. And so fairness can then be bounded whenever the problem local curvature is constant across all the entities, since the variance is also constant and bounded. And so this has a really strong implication, because this implies that perfect fairness cannot be achieved if those allocation problems or those problems in general is any non-convex function, as is the case for our motivating allotment problem and any other problem that essentially we studied. And so even adding Laplace noise to the inputs of this motivating example here will necessarily introduce fairness issue, despite the noise being unbiased. We can also derive a positive corollary from it, which is that if the problem is linear, then our mechanism is linear with respect to the problem. And now this result motivates us to develop some mitigating strategy to resolve some of those fairness issues. Now note, this issue here is not data dependent. So it's not a bias coming from the data. It's really the problem structure that magnifies errors for some groups more than others. And so a possible solution here that we devised is that of linearizing the problem of interest. So for example, in our allocation problem, this problem here is linear for the xi, with respect to xi, but not with respect to its normalizing term in denominator. So if we were to release this normalizing term as a public information or even privately, then this whole problem here would become linear. And so those plots show the results for this simple solution. The pink bars here depicts the unfairness, so the fairness violation that we have for the original problem that takes as input this noisy data set, right? So this is the difference in terms of bias of any two districts. And the green bar here, which is at 0, denotes the unfairness of this linear problem. And when also we are analyzing the error, we notice that there is essentially no noticeable difference in error in between the pink and the green bar, which is nice, as it tells us that this type of linearization techniques comes at almost no cost, despite achieving zero fairness for this particular problem in this particular data set. But we're also interested in other type of problems. And so let us look at the following problem. So the Voting Rights Act of 1965 provides a body of protections for racial and language minorities. Section 202 describes the conditions under which local jurisdiction must provide minority language voting assistance during an election. So this means that a jurisdiction needs to provide language assistance, which means that they need to translate voting registration, ballots, instruction in the minority language of interest if this decision rule here returns true. And this decision rule is a function of the number of people living in this jurisdiction that are speaking the minority language of interest, those that in addition have also English language proficiency, limited English language proficiencies, and those that also have low-grade education. So if we take a look at this plot on the bottom right, we're illustrating here the decision errors as absolute bias on the y-axis for the Hispanic language sorted by this quantity, the number of people speaking the Hispanic language over the districts. And the errors are on the true positive, which are particularly important because misclassification here implies potentially disenfranchising a group of people, of the individuals. And so the figures shows that there are significant disparities in errors and that those errors strongly correlate to the distance to this threshold, 10 to the 4th. And so this is really interesting because essentially it tells you that just because you're living in a district that contains a number of individuals that is close to an arbitrary set threshold, that puts you in a risk of having larger errors with respect of whether or if you were living in another region, which maybe had more individuals. And so we ask, why are those disparate impacts arising? Well, let's first take a look at these ratio functions here. So when we compare three counties, Loving County in Texas, Tarrant County in Texas, and Union County in New Mexico, they all have similar value for this ratio, 0.005, 0.005, 0.00484. So what we would like to see here, these blue numbers are the original ratios, and these red crosses here are the expected values for the noisy ratios. What we would like to see here are those red crosses to be on top of the blue numbers, which means we have an unbiased estimator for this ratio. But what happened is that while those two counties here have quite precise estimators, the first one, Loving County in Texas, does not, which is weird because they all have similar values. And so when we inspected why this was happening, we noticed that the number constituting numerator and denominator for those entities were substantially different, and those small perturbation into smaller numbers obviously causes larger disruption than if we're applying the smaller perturbation into larger numbers. And so this is significant. There is also another surprising result, which relates to the composition of Boolean formulas. So take, for example, the formulas modeling those threshold functions here in this allocation problem. If we plot the error, the bias, by each of this allocation, of each of these threshold, so those blue and pink points, you notice there is some bias, it's not that high. However, if we are connecting them under a logical operator AND, the bias increases substantially. And the same behavior actually occurs if we're using other logical operators. And so this is interesting as compositions really is a fundamental technique for us to reason about complex programs. And here we are saying that composition is affecting bias substantially. And actually, we don't even have an upper bound here. So this is really, really important. Now, what can we do? What can we do to mitigate this type of issues? Well, this is a much more difficult scenario, but we could resort to the same linear approximation trick. And so this is what we did. So essentially, we partitioned these data sets into population sizes of meaningful sizes, but arbitrarily. So we did this privately. And then we use the features of each of this group. So the number of people in a jurisdiction speaking a minority language of interest, those with limited English proficiency, and those that have low-grade education, and so on. So we take those features and we train a linear classifier that are using linear regression or a super vector machine model. And then we took the weights of this linear classifier and we use them as a proxy for our decision problem. And so when we're plotting then the errors in unfairness, and we're comparing the blue curve, the blue bars, which is the unfairness that we're obtaining by using the original problem and the noisy data, against the problem derived by this type of linearization technique here, then we notice that we're obtaining much less bias if we're using this type of linearization technique. Now, this is good if we can partition the data sets in such a way, but if we're using this technique on the data sets unpartitioned the way it is, then the reduction of bias is not that substantial. So those are interesting results and interesting issues because they relate the problem, they relate to the problem structure, the problem of interest. But then we ask, is this all? And now recall in the previous part of the talk, I talk about post-processing, about constraint-based differential privacy. And so we also asked, is there an effect of post-processing on the problem bias? And so take the census application again. So we have these data sets which feature some constraints, including non-negativity, integrality, hierarchical properties. And so post-processing redistributes the noise to restore fidelity. And the figure here on the right shows a histogram of some arbitrary counts. So the y-axis is the frequency of the count, and this is just an enumeration of it. The second plot shows the residual error after the application of Laplace noise to guarantee privacy. This plot here shows the residual error after a simple projection to non-negativity, to ensure non-negativity. And this last plot here shows the residual error after a projection step that also ensure consistency among parent-child relationships. So as I mentioned earlier, the error reduces. And this is quite drastic. As you can see, the variance here reduces. However, notice also that this variance here does not reduce uniformly across all entities. Thus, this creates potential for disparate impacts. And so we asked, why is this happening? And the blame here is to be given to the non-negativity constraints, as we've shown in our recent work at AAAI. So we can bound the bias which is caused by those non-negativity constraints by observing that there is essentially an N1 ball of a certain radius that is centered in our data of interest, which constitute a feasible subspace where there is no bias, and then we can look at the distribution outside this ball and upper bound it. So if we're looking at a figure like this, which reports the distribution of the Laplace residual error in blue and the post-process version in orange for some counties, so we can see that there is a lot of bias in the post-process residual error. But if we're starting shifting all the number by 5 and then by 15, then this error here decreases. So shifting actually increases the values of this radius, and the bias progressively disappears. So what does this mean practically? So firstly, using post-processing reduces the variance of the noise differently in different regions. And regions with many subregions, like counties, census block, and so on, they will have more variance than regions with few subregions. And so this creates situations where counties will be treated fundamentally differently in decision processes. So for example, take Arizona, about 2.4 million people in 15 counties, and Texas, about 8.9 million people in 254 counties. There is a difference of 6.5% in variance, which obviously might affect substantially the result of an allocation. And so those results may have strong implication with respect to group fairness, and we're using them to inform statistical agency about the trade-off between the granularity of the released data, the bias, and variance. This is just a teaser slide. We also have analyzed fairness and bias due to privacy in ML algorithms, including stochastic gradient descent. And what I won't talk about this in this talk, I'll be happy to chat about it offline. So some conclusion, this talk was motivated by the use of rich data sets combined with the adoption of black box algorithms that has sparked concerns about how the system operates, especially in regards of privacy, fidelity, and fairness. So we discuss some challenges that arise when using differential privacy for practical problems in data release, and to introduce a technique, post-processing techniques called constraint-based differential privacy, which ensures private data release, faithfulness to the problem structure and constraints, and accuracy. But also, we proved that several decision problems with significant societal impacts exhibit inherent unfairness when are applied to a differentially private release of the census data. And so just a few personal points on CP and how CP can aid in differential privacy. So the differential privacy research is largely dominated by theoretical results. And one of the long-standing goal of differential of DP is releasing privacy-preserving data that satisfy constraints derived from the data, so such as in hierarchical data sets or from a problem of interest. But CP instead thrives with the presence of those constraints. And so I believe that this community can contribute to improve the applicability of differential privacy to problems in which constraints arise, find new avenues where privacy might be adopted, transfer programming languages expertise to generalize and simplify the use of differential privacy algorithms in many domains of interest. And also the fairness and the bias issues that I've mentioned are still poorly understood and have not received the attention that they deserve, given their broader societal impact. And thus there is a critical need to have a close cooperation between privacy and optimization experts. So I'd like to thank you, and I'll take questions.
Thank you so